Hi Chris.
Hi Nick, how's things?
Good, thanks. But I think there's some real problems with the way we teach formulas.
Why? What's the problem?
Well, formulas and diagrams are very useful, but I think for the students it's just something we point to when we try and explain things.
But formulas are really important. They're a very concise and precise form of communication. They hold a wealth of background information, and they have limits and they have boundaries, and anybody who understands the language of formulas sort of gets this information very quickly.
Exactly. But we don't really teach this.
Well, of course we do. We have lectures, and the lecturers go through where the diagrams and the formulas come from, and you talk about them in assignments. They're in the textbooks. Look, they're all through this thing here.
That's all very well and good if you really understand the physics behind it, but when you're just learning it, they can just be a bit bewildering and you don't really see what they're there for.
So what you're saying is that the formulas, even though I see them as a very condensed way of understanding something, the students don't know that because they haven't got the background physics.
Exactly.
Maybe if we started with the formulas and unpacked the formulas, then the students would be able to get an inkling of the physics that's behind them. Perhaps if we started with something like F equals ma. You've got your pad there. Let's have a draw with that. Okay, so this F here is force, and it's a vector, and it's in units of newtons. M is mass, and it's in kilograms, and it's scalar. Acceleration, which is in meters per second, and that's also seconds squared, sorry, it's also a vector. Okay, so this is our basic formula. What does that tell you? Where does that come from? What branch of physics?
Well, it's going to have to be something to do with mechanics, the motion of objects and the changing of its energy.
All right, so if we've got that background, then what can you tell me from this particular formula?
Well, if we have a mass and we apply a force, the object's going to accelerate, so it's going to change speed or direction.
Okay, so anywhere you see an object that's changing its speed or its direction, you know that there's an unbalanced force applied to it.
Yes.
Okay, let's say we have my little car in the parking lot there, and it's not working, so I've got to give it a push. We apply a force to it, and it causes the mass of the car to accelerate. All right? What if my mate gives me a hand to push the car? What will happen then?
Well, you're essentially doubling the force, aren't you? So you'll get a much greater acceleration.
That's right, because the mass is constant.
Yes.
What if we had a ginormous mass? What type of acceleration would we get for just one person pushing it?
Well, we'll get a much smaller acceleration, wouldn't we?
A tiny little acceleration. Okay, can you think of any limitations on that?
Well, what if the opposite? This was very small. You wouldn't be able to even see it, or let alone give it a nice controlled push.
Okay, good. Now can't keep going. What else?
What if someone had stolen the wheels? Then good luck posing friction in that case.
Okay, so what we've got happening here is we have a formula. We can ask the formula questions about what happens if I increase that, what happens to the other bit, if I change this, how does that happen? What underlying assumptions have we got for this one?
So that we're always in contact with the mass, that the two people push the same way, that there's no friction.
Okay, but something else. Come on, I'll show you over here. I've actually been thinking about this, and you might be surprised to find that I've already whiteboarded a lot of these things you've been thinking about. Now this is rather complicated, so I better take you through it. What we've been assuming here is that our force is in the direction that we want the motion. Okay, so it's greater than zero, it's along the axis that we're moving. And we've also assumed that it's a constant force. The force isn't changing, constant in size and constant in direction. So we have also assumed that our mass is constant, and therefore it all keeps going in the same direction. But there's many other scenarios besides that one. What if there was no forces at all? What if the force was in the opposite direction to motion? What if the force was at some sort of angle to the motion? What makes things go round in a circle? There's got to be a force there because you're changing the direction that it's going in. What if the force isn't constant at all? So in these situations here, we've said, yes, the force is constant in its direction and it's constant in its magnitude. For circular motion, we're saying no. Why are we saying no for circular motion?
Well, it always has to be changing direction, doesn't it?
That's right, it always has to be pointed towards the center of the circle. And this is an interesting one. Let's sort of think of, it's not going to have the same direction and it's not going to have the same magnitude. What sort of forces do we get then? What sort of motion do we get then?
Changing accelerations.
Yes, and that would be like when you have a spring. So the further you pull it away from its origin, the harder the forces. What about when you have two objects that are being pulled together, just like you're being pulled to the ground now? That strength of that force depends upon the distance between the objects. So what we have is, it's not got a constant direction because the objects can be moving, but it's always between the two objects, and it may not have a constant magnitude because it depends on how far away they are from each other. Up until now, we've always had a constant mass as well. What happens if the mass is not constant? If the mass is not constant, then you're looking at something like an explosion. And so what sort of forces are we dealing with then? Those are the types of questions you could ask of this very, very simple formula, F equals ma. Do you reckon that your students could handle this?
I really think they could.
Okay, well,
Thank you so much.
I've got to get back to my book.
Thank you.
See you, Nick.